Welcome to The Explainer. Today, we're jumping right into a question that's at the very heart of orthopedic surgery. Why do our implants fail? We're going to unpack this constant battle between the raw mechanical strength an implant needs to survive and the biological harmony it needs to thrive inside the human body. And this right here is the million-dollar question. It's the core design challenge in all of arthroplasty. You're walking this tightrope between pure engineering, making an implant that just won't break, and the really complex biological needs of the bone it's sitting in. If you're heading into your Viva, being able to explain this balancing act is, well, it's absolutely crucial. So let's really break down this trade-off. Think of it like this. On one side, you have a super stiff implant. Great, it's got fantastic resistance to fatigue failure, it can take millions of steps without breaking. But, and it's a big but, that very same stiffness shields the bone from the stress it needs to stay healthy. On the other hand, a less stiff implant is great at transferring load, but you have to ask, does it have the mechanical guts to survive for decades in the body? So here's our game plan. We're going to tackle this step by step. First, we'll get into the science of fatigue failure. Then we'll lock down what the endurance limit is. After that, we'll look at the biological headache of stress shielding, see how modern designs try to fix it, and then wrap it all up with a masterclass to make sure you nail this in your exams. Okay, first things first. Let's really define the main enemy we're trying to defeat here, fatigue failure. And you have to understand, this isn't about one big traumatic break. It's a much more sneaky process. So the key takeaway here is that it's not a single, huge force that snaps the implant. Nope. It's the slow, steady accumulation of damage from millions of tiny, repetitive loads. Literally every single step a patient takes. And even though each one of those steps is way below the material's breaking point, that repetition is what allows microscopic cracks to start, grow, and eventually, catastrophic failure. So how on earth do you design something to fight against an invisible enemy like that? Well, engineers needed a roadmap, right? A way to actually predict how long a material would last under all these different loads. And that need led to a really foundational tool in material science. And this is it. This is the SN curve, sometimes called a Wöhler curve. You can think of it as a materials fatigue cheat sheet. It simply plots the amount of stress on the vertical axis against the number of cycles it takes to fail on the horizontal axis. And you can see that relationship right away. The higher the stress, the fewer cycles it takes before something breaks. Now, we can really chop this curve into three main zones. First, you've got this steep downward sloping part, the finite life region. It's pretty straightforward. More stress equals a shorter life. Then you get to this transition knee, where things start to level out. But for what we do, for designing an implant that's supposed to last a lifetime, it's that third zone, that flat horizontal part, that is the absolute holy grail. Okay, so let's zoom in on that holy grail zone, the endurance limit. If we're talking about an implant we expect to last for 20, 30 years, understanding this concept is literally everything. The endurance limit is basically a safety zone. It's the stress level below which, in theory, fatigue failure just won't happen. Now think about a hip replacement. That's maybe 1 million walking cycles every single year. For that implant, designing below this limit isn't just a nice idea, it's an absolute necessity. It is the single most important property for long-term mechanical survival. And here's the number to tattoo on your brain, 20 million. The design goal is simple, but it's profound. You have to make sure that all the peak stresses happening inside that implant stay safely below the endurance limit for at least 20 million cycles. That is the benchmark for a 20-year implant. But, of course, there's a huge catch. The most obvious way to guarantee a high endurance limit is to just make the implant super stiff and bulky, right? Well, when you do that, you solve the engineering problem, but you create a massive biological one. In protecting the implant, we've started a war with the bone. And that problem is called stress shielding. It's a direct consequence of Wolff's Law, which we all know says that bone remodels based on the loads it feels. So when a really stiff implant takes on most of the load, it's basically shielding the top part of the femur from its daily workout. And without that stress, the bone just says, well, I'm not needed here, and it starts to waste away. The root cause here is a fundamental mismatch in what's called the modulus of elasticity. That's just a fancy term for a material's stiffness. Metals like cobalt, chrome, and titanium are just way, way stiffer than our cortical bone. Because of that mismatch, the implant acts like a rigid pipe, bypassing the bone, carrying all the load, and leaving the surrounding bone feeling, well, unemployed. And the clinical fallout from this is serious. This bone loss around the implant leads directly to aseptic loosening, which is where the implant just loses its grip, and ultimately the implant fails. Not because the metal broke, but because the biological foundation it was built on just crumbled away. This is a huge reason for late-term implant failures that need really complex revision surgeries.
So, what's the solution? How do we build an implant that's tough enough to last for decades, but also flexible enough to play nice with the bone? This is where modern implant design gets really clever. It's a sophisticated balancing act between the mechanics and the biology.
So the thinking has really evolved. We've moved away from just brute force stiffness and more towards intelligent designs. Instead of those old school solid, rigid stems, now we're seeing implants with porous metal structures, often made with 3D printing. The whole point of these designs is to be intentionally less stiff, so they can share the load more naturally with the bone. And the magic word here is osseointegration. By creating these porous surfaces that bone can literally grow into, the implant and the bone become one single functional unit. This is huge. It not only gives you amazing biological fixation, but it also protects the implant. By spreading the load out more physiologically, you can slash the peak stress in the metal by over 20%. And what does that do? It makes the implant much more resistant to fatigue in the long run.
Okay, let's bring this all home. We're going to distill this down into the high yield points you need for your Viva. This is how you show your thinking at a consultant level.
This quote right here, it's the perfect summary of stress shielding. It draws a straight line from the implant's presence to the reduced load to the bone loss. If you can explain that causal link, you've mastered the concept.
Now, let's talk about a few common traps people fall into. First, please do not confuse stiffness with strength. Stiffness is how much something bends. Strength is how much it takes to break it. They are not the same thing. And here's a real top-tier point. You need to know that unlike steels, a lot of non-ferrous alloys don't actually have a true flat endurance limit. Their SN curve just keeps sloping gently downwards forever, and that's a massive deal when you're designing with them. And here are the words you want to weave into your answer. Using these correctly just shows you get it on a deep, mechanistic level. You can even chain them together. Stress shielding is really an application of Wolff's Law, caused by the modulus of elasticity mismatch. Modern porous designs try to combat this by promoting osseointegration, which in turn prevents periprosthetic bone resorption and the ultimate clinical failure of aseptic loosening.
And finally, I'll leave you with a question to chew on, something to show you're thinking ahead. An implant's fatigue properties aren't set in stone. As that bone grows into it, the mechanical behavior of the entire bone implant system changes. That SN curve we test in a lab is for the metal alone, but inside the body, it becomes a living, evolving composite. Understanding that dynamic change, well, that's the future of implant design.